Welcome to the IRENA seminar, the first seminar of this, I guess not the calendar year.
Academic year.
Academic year. Yeah, so welcome to this academic year's seminar. We're very excited that we have, again, a great committee of young researchers that put together the program. And we're excited to see all the presentations this year. So this is kind of, I don't know if it's unique, but I think it's one of the great things for IRENA that the young researchers have the opportunity to take on some leadership roles. And we're really happy that this group here, I'll be sharing the picture. We do, right? Yes.
Yes.
That this group has stepped up, and I really hope, I mean, this is a lot of work, but I hope it's also a great opportunity for you guys to, it's meant to be an opportunity for, of course, networking with the speakers. You also have a lot of freedom choosing the speakers that you're interested in to hear from. So I think that's also nice. And you all represent different networks in astrophysics across the world. And so I hope there are also interesting opportunities from being able to sort of network within the committee and, meet some young researchers from other networks that, you may encounter in the future, in your future careers. And you can already build sort of your first contact. So I hope this will be a good experience for you guys. And I'm really looking forward to the program. I think you did already a great job with the first talk. So I'm very happy to hear from Mike. And I don't know, who's here from the committee?
I'm here hosting for this session.
Okay, so there's Alred. Hello, thank you. Is someone else
Cameron.
could say hi?
Yeah, so I'm here as well.
Cameron, you're from Kanpan, right?
Yeah, so I'm a postdoc based at Triumph.
Okay. Nice to meet you. Anybody else? Okay. Okay, I think ready to go, and I hand it over to the chair of this seminar, which who's chair? Alred. Okay, so Alred, I hand it back to you, and thank you guys again for doing this important work.
Yeah, thank you so much, Hendrix, for the generous introduction to the series. So on behalf of the Online IRENA Seminar Organizing Committee, I welcome you all to this series of what's going to be very exciting presentations and updates for this year. So the first speaker for today is Professor Michael Zingale. He's a professor of physics and astronomy at Stony Brook University. He earned a BS in physics and astronomy from the University of Rochester and a PhD in astronomy and astrophysics from the University of Chicago. He was also a part of the Flash Code development team that won a Gordon Bell Prize in 2000 and received a Presidential Early Career Award for all scientists and engineers through NNSA in 2005. He also received the Outstanding Junior Investigator Award for the DOE Office of Nuclear Physics in 2006. So Michael's research involves the development of new algorithms for efficiently modeling convection in stellar interiors. He is a co-developer of the open source astrophysical, multi-scale, multi-physics simulation codes, Castro and Maestro EX, and the nuclear astrophysics library pynucastro. He applies these codes to study early phases of type 1a supernovae, novae, and X-ray bursts. We are very happy and excited to have Professor Michael Zingale giving the first talk for this series, and I welcome Michael to share his screen and take us away.
Mike, you're muted.
Sorry. All right, there we go. It's been how long since COVID, and I still don't know how Zoom works. All right, hopefully you can hear me now.
Yeah.
I thank you for having me. I'm going to talk about our library, pynucastro. I'm going to talk as well about how we use it for some science problems, but I mostly want to devote the time to discuss the community aspects of what we're hoping to do with this Python library called pynucastro. I am going to try to do something interactive live. And if you follow this QR code, it'll bring you to a Zenodo link, and you can download a notebook that I will step through and play along as well. And let's just hope that my computer cooperates. There's a bunch of people who helped develop this library. Some of the names are listed there, and you can see more if you follow to the GitHub link, which I'll have sprinkled multiple times. Okay. All right, so pynucastro is a library. Stands for Python Nuclear Astro, not very imaginative. That we want to use as a way to explore nuclear astrophysics data. So reaction rates, properties of nuclei, when certain burning processes are important. We want to be able to do this interactively in Jupyter, and we want to be able to output reaction networks that once we have a feel for what we want to do, that are optimized to run in simulation codes. And these days it means reaction networks that run on GPUs. And so we want this library that can output C++ code that can plug directly into our simulation codes. And finally, we want to use this to for education. So we want to be able to have simple interactive ways of explaining some of the concepts in nuclear astrophysics that come up when we're teaching our STARS class. In fact, that was the motivation for this originally. Almost 10 years ago, I think it was a take-home final exam, I gave the question, write your own CNO network. So go find the reaction rates. I pointed to Coughlin and Fowler and pointed to JINA-CEE and said, download these, write some code to solve the system of ODEs and evolve CNO and see what happens. And no one did it, sadly. And no one did it because they all told me they looked at the rates and they said, well, you know, it's a lot of work to get those into a form that we want to be able to use inside of our codes. And so in my stubborn way of doing things, my solutions for that became the initial version of this library. So I'm not going to spend too much time on why Python and Astro. Python's taken off. It's well supported. Most students learn it. But for our purposes for this library, the scientific Python ecosystem provides the libraries that we can leverage to make our life easier. So we're going to make use of a lot of existing tools that are out there, and we're going to build a library for nuclear astrophysics on top of it. The entire library is developed openly up on GitHub. You can go to github.com/pynucastro. That's the umbrella organization. The actual library itself is in a repo called pynucastro, but we also have some presentations and some other stuff in that organization on GitHub. It's on PyPy. You can say pip install pynucastro. It's on Conda Forge. You can say conda install Conda Forge pynucastro, and you can install it. In prepping for this talk, we released a new version just yesterday. It's already up on PyPy. It's building, I believe, on Conda Forge, but it just cleaned up some stuff that I found when I was putting together that notebook that we're going to look at. Python's an object-oriented language. And so we have some building blocks, some core building blocks that we use in pynucastro that we can then build richer and richer libraries, descriptions of rates, or complex networks from. And so the four main classes that you'll see in the example that I'm going to show in just a second are a nucleus, pretty self-explanatory. It knows the basic properties of a nucleus. It also knows things like the partition function, so it can interpolate from tables of partition functions. It knows spins of the nucleus. Rate, basic rate just knows reactants and products, but we can build classes from that. A reactlib rate knows about the set format of reactlib rates and how to evaluate those. A tabulate rate knows how to interpolate from a table of rates. We have derived rates that know how to do detailed balance from a forward rate, and we have approximate rates that know how to approximate out some of the nuclear physics. Again, all built from that. Libraries are going to be collections of rates. They provide methods for filtering, a rich set of methods for choosing exactly which rates might be applicable for us. And a rate collection is our base class for a network. And on top of this, we have lots of different types of networks that provide some specializations, including one that outputs Python code and one that outputs C++ code. So rather than looking at all of that, we're going to walk through things, and I'm going to show you a notebook, and I'm going to show you a lot of the capabilities that I discuss here. We'll see how you can build and explore networks within a Jupyter notebook. We'll see this later on, not interactively, how we can approximate rates or modify the endpoints of rates, because often in simulation codes, we want to create as small of a network as possible that still does the nucleosynthesis that we want. We'll see how to find unimportant rates, and this is something that we actually have a more elaborate method than I'll show you today. We can derive reverse rates via detailed balance. We can create custom rates. This is something that came from an issue. Someone wanted to be able to create just a simple power law rate, and it's easy to do if you just subclass our rate class. Solve for nuclear statistical equilibrium, and then with one line, you can write a table that basically tells you as a function of density, temperature, and YE what the equilibrium states are, which you can use to interpolate a simulation code. Export code as Python or C++. You can interface with Julia solvers. It turns out Julia has a much richer set of ODE solvers than is available in Python. And you can interface with machine learning libraries because most of those have Python wrappers. And so this allows us to do explorations of some nuclear physics properties using neural networks. I'm not going to show that. Again, if you capture this QR code in the corner, it'll bring you to the Zenodo record. You can download a Python notebook there that I just uploaded today. Fingers crossed it's going to work for all of us. And you can play along with what I'm going to show you. You might have to pip install pynucastro before you do that. We have extensive documentation online, and we're continually adding to it. As I said, one of the things that we want to do is we also want this library to be able to be used for education. And so one of the things I'm thinking a lot about now, because I'm teaching stars again, is what sort of notebooks can we create that show how some different stellar processes work. And we're starting to add some of those on there. So without further ado, I'm going to try to go to my notebook, which appears to be up and open. So I'm inside of Jupyter. I made it full screen, but this is just a basic Jupyter lab environment. And I'm going to import pynucastro. Let me make this, let's see. I'll make it one more bigger, and then I might regret that, and I might make it smaller for some plot. But I'm going to import pynucastro, and we normally, as we import it, we rename it just because it's less typing to PYNA, pynucastro. And the first thing we'll look at is we'll look at a nucleus, and we can create a nucleus easily just by giving a name like nickel 56. You can make it caps if you want, but why use another key? And we can access basic properties, right? We can access Z and A for the nucleus, proton number, and atomic weight. We have the tables from Rauscher's partition function work that extend to high temperature for a lot of nuclei. And so from that nucleus, we can look at the partition function and we can evaluate it at a temperature of 5 billion Kelvin. And we see slightly greater than 1. And as we increase this, it starts to increase as well. And we can get the ground state spin states as well, which we pull in from the atomic mass evaluations, which we need if we're going to create derived rates. So nuclei know a lot about a nucleus. We can load a single rate from ReactLib. If you go to the ReactLib website, you can download a rate and it gives you something that looks like this. So this is carbon-13, capture proton, release a gamma, nitrogen-14, and it's from this NACRA compilation. We don't normally work with the individual rate files, but here I'm working with just an individual rate file to start. And, if I print the rate, it looks like something that is readable to me as a human. So it looks like what the reaction rate looks like. Rates know about the nuclei that make it up. These are actually nucleus objects, the proton and carbon-13. If I look at the products, those will be a list of nucleus objects as well. And I can evaluate the rate. And at a temperature of 1 billion, it's about 4,000 in CGS units. Often we want to, if we want to do sort of scaling, dimensional analysis, we want to express the rate as a power law, some constant temperature over some reference temperature to some power nu. I can compute what that power nu is around the temperature of 20 million Kelvin, and it's the power 16. So this is the slowest rate in the CNO cycle, and this is saying that the temperature sensitivity of that is T to the 16. That's usually what we teach people in class, and you see we can recover that from the library. We can plot the rate as well. So just use the plot method, and this is what the reaction rate looks like, the temperature-dependent term of the reaction rate versus temperature between 100 million and 10 to the 9 Kelvin. And you can change the limits by passing different arguments into the plot function to examine it around any point. If you look at the plots that are nicely embedded in the ReactLib webpage, this looks like it as well, which is a good thing. So it looks like we recover what they do. Now for the fun stuff, if I want to use this in Python, I can say, from that rate, give me a function string that's in Python that can evaluate the rate. And here you see it's looping over the sets that make up the rate. This one has 2 resonances. It loops over them. And these are the different terms that get added together to make up the full rate. And it wrote out the Python code for me. Likewise, if I want to do C++, it's more verbose. We use a lot of templating in C++ to hide some stuff if it's not needed. But this is C++ code that can that can be used to evaluate the reaction rate. These are building blocks. When we build a network, each rate is responsible for writing out its own code that is used to evaluate that particular reaction. So far, nothing's crashed, which is nice. We're going to do 2 examples. One example of looking at a hydrogen network and one example of looking at nuclear statistical equilibrium. So to build a hydrogen burning network, we want to pick nuclei that we believe are important in proton-proton and in CNO burning, and maybe hot CNO. And so I can read in all 80,000 ReactLib rates. It takes a few seconds, and it's done. And it reads them into a library. We have in pynucastro, we have downloaded the ReactLib library, their latest release, but you can use a different release if you want. And then what I'm going to do is I'm going to say these are the nuclei I care about: proton, deuterium, helium-3, helium-4, carbon 12 and 13, nitrogen 13 through 15, oxygen 14 and 15. Those are what are usually involved in hydrogen burning. And I could say, take that reactive library and find all the rates that link the nuclei in that list together and give me all those rates. By default, it'll give me forward and reverse rates. We'll see in a moment those reverse rates probably aren't very interesting for us if we're just doing hydrogen burning. I could turn them off at this filtering level, but I don't just yet. You can also filter by saying, I want these just to be the reactants. And so it'll pull in rates where the products are not in this list, but use this list of nuclei as the reactants. And so there's lots of different ways that we can filter the 80,000 rates in Reactlib. Once I have a library, I can make a network. I'm going to make a Python network because I'm going to want to integrate it just all in Python. I just pass in a library. I can pass in a list of libraries. And I can look at it, and these are the rates that it pulled in. It pulled in quite a few rates. Some of these rates probably aren't going to be important. The reverse rate of triple alpha probably isn't going to be very important. The forward rate of triple alpha probably isn't going to be very important if I'm just at the temperatures where hydrogen burning is happening. We have a lot of different ways to plot networks and examine what's going on in a network. The most basic plot, and we use network X under the hood to represent the network as a network. I'm going to zoom out just a little bit. Shows all the connections between the rates. Z on the vertical axis, number of neutrons on the horizontal axis. You can see all the nuclei or nodes, and all the connections between them are illustrated in here. If I evaluate the rates, I need to specify a density, a temperature, and a composition. So I'm going to pick a density and temperature that are appropriate for the center of our sun. The composition, in pynucastro, we have a composition object. You have to tell it what nuclei you want to represent. So I'm just going to give it the nuclei that are in this network. And I'm going to say, make it somewhat solar-like. It's not exactly, solar-like, solar. So that's one of their goals later on, is to actually know about a real solar composition and do a better mapping here. But this is enough for us to evaluate the rates. I can evaluate each of the rates. And if I do that, I get a dictionary keyed by the rate. This is what the rate object prints out as. It actually prints as its nice human readable form, but this is a rate object as a key. And the value in the dictionary is the actual reaction rate in ergs per gram per second. No, this is reaction, not energy. So in number of reactions per second. You can see some are just not important. Some are really, really small, like the forward rate for triple alpha. I can color my plot by those rates. So here's those links again. I've made the edges curved just so the forward and reverse rates aren't on top of each other. And I can see that the magnitude of the rate spans 300 orders of magnitude. So some of these rates are just not at all important. Again, here's that reverse rate for triple alpha. It's probably not going to do anything. It's the purple one. But you can see there's a lot going on in CNO, and there's stuff going on in proton-proton. So I can see some rates are clearly important under these conditions, and some just aren't going to be important. We have some ways to filter this out, because again, I come from multidimensional hydrodynamics. We want to use small networks because every species we have in our network, we have to advect in 3D. So it means we have to have memory for it, and we need to solve a continuity equation for it, and that takes resources, computational resources. So we'd like to reduce the network if we can. We'd like to reduce the nuclei if we can. We have a more advanced way of doing this that I'll mention just in passing later on, but here's a simple way to do this. I can create a list of thermodynamic conditions. Maybe this is sampled from a simulation. And I can have as many as I want. I have 2 here because I didn't feel like typing. But here's the sun. Center of the sun, density of 150, temperature of 15 million Kelvin. I'm going to keep the composition constant just for this notebook because I didn't feel like changing it. And then more dense and hotter. I'm going to add a tuple of density, temperature, and composition for that. I'm going to pass in that list of thermodynamic states. And I'm going to say, give me any rate that never gets within 10 to the minus 30 of the fastest rate in here. So this is a relative 10 to the minus 30. And it does that. And it finds these are the rates. So these rates are basically never important for the list of thermodynamic conditions that I passed in. And I can remove them. And then I see my network is much smaller. If I plot it now, I'm plotting at a higher temperature. I can see there's a lot fewer connections. Most of those purple connections went away. The triple alpha stayed. It just made my cut. But most of those connections went away. I can see at this higher temperature, this is 150 million Kelvin, that I'm in a regime where when I'm in CNO and I capture a proton, make nitrogen 13, the hot CNO is now active. Capture another proton faster than the nitrogen 13 decays. And so I can see visually on here that at this temperature, I'm going to be in hot CNO. And I'm going to start to be limited by those beta decays. There's other ways to visualize our network. This is given the very descriptive name called network chart. But for each rate and for each nucleus, it basically just colors them by how much each rate affects each nucleus. We can plot them on a grid. This is good for when you have lots and lots of nuclei. And we can color it by different quantities. This is colored by activity. Activity is the sum of the flow through that nucleus. And so creation and destruction add together. So this is really showing the flow through the nucleus. And what's cool, and this is true for most of our plotting functions, you can pass it a filter, a function to filter out nuclei that you aren't interested in. Here we just use a lambda function and say, only show me nuclei where Z is greater than 2. So cut out the proton-proton part just to make this a little bit more compact. And we're seeing what's happening around CNO, where most of the flow is in the CNO. When we're happy with our network, we can write out the code that is needed to integrate it. Just like a rate can write out the Python code or the C++ code needed to evaluate the rate, a network can write out the code that's needed to evaluate the right-hand side. So for instance, I can get the y dot string for carbon-12. And this is what the ordinary differential equation for carbon-12 looks like, at least in the way that we think about it in pynucastro. dy dt would just be a NumPy array for carbon-12, destruction due to carbon-12 plus protons and nitrogen-13, creation due to nitrogen-15 plus proton, and creation due to triple alpha. And you see it has the density terms in it. It has the counting factors that you need in it, has the molar fractions and the correct powers. And it can do this for all the nuclei. And so with this, we can write out the right-hand side of our reaction network, which is needed for integrating the network. And again, we could do this in C++. It's uglier, but it works just as well. When we're happy, I can write out the network. When I do this, it writes it to a file that is a Python module that I can import. You can look at the file. If you want to look at the file, you can uncomment this line. And you can see it sets up all the metadata. It knows what the... I'll just quickly go through it. Not quickly, because it's a lot of scrolling. That's why it was commented out. sets up indices to index into the arrays to know what each nucleus are, atomic properties, the masses of each of the nuclei, how to compute the energy, a function to compute the energy release. I didn't mention this, but we use Numba. Numba is a just-in-time compiler for Python. It takes a second when you first load it to actually compile the Python code into machine code, but then it runs really fast. And for integrating a network, you want to use Numba because you're going to be calling the right-hand side often. And then here's the functions for each of the rates that we need to evaluate. So this is, I think this is the one we looked at earlier. And then there's a right, we could screen as well. If we pass in a screening function, it'll call the screening function and it'll modify the rates according to the screening. And then here's each of the terms of the system of ordinary differential equations written out for us. And the Jacobian written out for us as well with the screening, all the Jacobian elements stored as a dense array. I can import that. So I just wrote it out. I can import it back in. I can load NumPy, and I'm going to use SciPy's ODE integration methods. Solve IVP is SciPy's initial value problem solver. Solve IVP, behind the scenes, has a lot of different methods that it can use. Reaction networks tend to be stiff, and so I'll use the BDF solver, which is one of the backward difference solvers. I just specify it as BDF. I can pass in the Jacobian. I can select some tolerances, 10 to the minus 8 for relative, 10 to the minus 10 for absolute tolerance. I'm going to burn for 10 to the 20 seconds. And I'm going to set my initial conditions to be mostly hydrogen, then helium, and 2% carbon-12. Convert them to molar fractions, and that's my initial conditions. It's going to take a second because it's got to do the Numba translation, but it's already integrated it. If I look at the solution object, it was successful. That's good. Called the right-hand side 1,500 times, called the Jacobian 44 times. And I can make a plot. And this is what we show in class when we talk about hydrogen burning. For instance, in the sun, these were the conditions in the sun. After about 10 to the 17 seconds, which is, few billion years, that's when you start to see the hydrogen start to be depleted, and you see the helium build up, and then everything's basically gone by the end. You can do more complicated networks as well. At some point, the solvers are going to struggle. One of the things we're working on is other integrators and ways to make the solvers, the integrators, have easier times with the networks by doing some rate reduction. These are projects that we're working on actively now. Again, for teaching, you can interactively explore your network. So here's that same network view. I'm going to try and get it all in frame. And I could change the temperature slider. This is log T, so it's 10 to the 8. Make it colder. It evaluates all the rates, and the plot changes dynamically for me. If I make it a little bit colder still, this is about where we are in the sun. At this point in the sun, well, this is higher density than the sun. At this point, for these conditions, you can see the normal CNO is dominating. Carbon-12 captures a proton, makes nitrogen-13. That decay happens faster than the subsequent proton capture. And so I do the normal CNO, but increase the temperature a little bit. I see that now those proton captures are competitive. Increase it even more, and I see that now I'm completely rate limited by these beta decays. And so these interactive visualizations of a network are a nice way of demonstrating some of the nuclear physics concepts. We can deal with tabulated rates. We have rate tables from Laganke and from Suzuki, and we could read those in just as well We can plot them. I'm going to go through this fast in the interest of time. Tabulated rates are a function of electron density and temperature, and we can evaluate those as well. Now we have to pass in the electron density, but that works just as well. And we can build networks that combine all these different rate types. For nuclear statistical equilibrium, we have something that we call an NSE network. Here's a collection of nuclei that are concentrated around the iron group, plus proton, neutron, and helium-4. I can build an NSE network. At the moment, it still thinks that it's going to use the rates, even though it doesn't solve for NSE using the rates. So I get a complaint here that, hey, one of these rates that I'm using, this neutron decay from ReactLib, you probably want to use a better rate, because if you're dealing with this under degenerate conditions, that's just pure decay. But I'll start with YE of 1/2, equal number of protons and neutrons. And I can solve for NSE and get the composition. And this is what the NSE composition looks like. I'm mostly nickel 56 because that's a symmetric nucleus, equal numbers of protons and neutrons, so it matches my YE, and some trace other heavy nuclei. If I decrease YE, I become more neutron rich. And if I solve at this new YE, I didn't mention it, but you can use screening effects in the NSE, which we're doing here. Now you see I'm more dominated by iron 56, and the nickel 56. It doesn't even show on here. It's in the other part of this exploded wedge here. So these are just a few of the ideas or features that the library can do, and you can see that within Jupyter, you can do a lot of exploration of reaction rates, of nuclear properties, NSE. And so you can learn a lot, and you can use this to help focus down on what nuclei and what reaction rates you think might be important for a simulation. Once you do that, you can output the network. And so I'll switch back to looking at how we actually use these networks. I think I only have like 15 minutes left. And so I'll talk a little bit about how we use some of these networks. Again, if you missed it earlier, you follow that QR code. I'll try to drop it in the chat afterwards as well. You'll get that notebook, and you'll be able to see everything that I just ran through. Most of what I just showed is also directly up in our pynucastro documentation. So if you want to, and the documentation is mostly just Jupyter notebooks. So you can download any of the notebooks from the documentation, and you can run through it there as well. All right. So as I mentioned, we're developed fully on GitHub with a BSD license. Every time we make a change, we run a lot of tests. We have pretty good coverage of our unit tests, so we make sure we don't break anything. We run through all of the notebooks and do answer testing on all the notebooks, and all those tests need to pass. And someone, a member of the development group, also has to approve every pull request before it gets merged. And if you look up on there now, you'll see there's a few that are sort of lingering, waiting for some approval. We have contributors not just here at my home institution of Stony Brook, but around the country as well. And we loosely follow a procedure that once you become a frequent contributor, you get included on code papers. So we've had 3 papers now, one JOS paper, an AppJ paper, and then a conference proceeding describing pynucastro. And so contributors who have earned contributor status are all co-authors on those. Every time we do a release, we drop a record on Zenodo, and all the contributors are listed in the Zenodo record. And you also get write permission and the permission to review pull requests. in our GitHub repository. We are, we'd love to have more contributors. Part of the reason why I wanted to give this talk, because there's a lot of useful things we could still add to the library, and I think it fits within the nuclear astrophysics community well. All right, here's just a summary of what we have at the moment. We started off with ReactLib. So we have the latest release library of ReactLib. We have then most of the rates that Zingale and Martinez Pinendo have released for weak rates, the Suzuki rates. Our choice of which rates we pull in is usually driven by what science we're working on. We have a gap here that we're going to fill in the next months. Sometimes there's special rates that appear in the literature. So C12 alpha gamma, there was a revised rate that appeared a few years ago. And as best as I know, that's not in ReactLib just yet. So we can add those in individual rates as needed. We added an alternate rates module that allows us to add those in. In this case of this one, thankfully, they use the same format as ReactLib, so it's very easy to drop in. We have 4 different screening routines. These mirror the same screening routines that we use in our main simulation codes. They largely agree with one another, but there are some differences, and so you can explore the differences there. We have someone using pynucastro now with machine learning to see if we can learn how screening works. We have nuclear data, masses, binding energies, and spins from the atomic mass evaluations. I think we missed the last one, and I think there's one coming out soon, so we'll update those. Temperature-dependent partition functions. I think everyone pretty much uses those from Roscher, and thermal neutrinos from the Ito et al. Stuff, which again, I think is pretty much widely used in simulation codes. But these frameworks can be added. You know, we can add other sources as needed by building on those foundation classes that we already have in the library. That list has some gaps, and that's because, you know, we're a finite number of people. And so we've prioritized what we've added to the library based on what our science drivers are. Mainly supernova, thermonuclear supernova, X-ray bursts, and novae are the things that we've been exploring. And so our coverage of what nuclear data we have supports those applications. If anybody has thoughts on other things we should add and maybe knows how to do it, you can open an issue. You can create a pull request. We can add you to our Slack channel if you think you want to contribute more frequently to the development, and we'd be happy to work with you. One issue that is sometimes unclear for us is that a lot of nuclear data doesn't have a license to indicate how it can be used. And so when tables appear with a paper, it's not always clear if we can use copies of those tables. And so in the future, indicating a license for the nuclear data so that it can be freely reused in libraries, I think would help not just us, but help any nuclear astrophysics library.
Oh, Michael, you have around 5 minutes.
5 minutes. All right. We have a lot of features under development, but I only have 5 minutes. And so I'm not going to go through all of them. I mentioned we have other reduction stuff. There's a technique from chemistry called directed relation graph with error propagation. We have this. This was added by some colleagues at Berkeley to pynucastro. It basically asks the question, if you remove a nucleus from your network and propagate through, the effects of that, am I still happy with that network? And this is something we've only explored a little bit, but this is a powerful way that you can take a very big network and reduce it down to something more reasonable. We want to add an EOS in the next couple of months, and we want to add more teaching examples. So in now 4 minutes, I'll just talk about some of the ways we use this in simulations, because again, that was our other big driver, is to be able to use what we build in pynucastro in simulations. We have a code called Castro that uses pynucastro. There's at least 2 other codes that are using it as well. Castro is written in C++. We have a library called AMRX Astro Microphysics that is what we drop the networks in that we create with pynucastro. This provides the integrators. It has implicit integrators and stabilized explicit integrators that work well with these networks. And it supports different ways of coupling them to hydrodynamics, and it supports GPU offloading. And pynucastro directly supports this by using the class AMRX Astro CXX network. There's a simple CXX network that doesn't pull in all the AMRX stuff, but doesn't have all the features. When you do simulations, you often want a small network. I mentioned that once earlier as well, because you don't want to deal with the memory of carrying all these nuclei. One things we do often in 2D and 3D is we create approximate networks. For instance, it's common to group together the alpha p, p gamma parts of a helium burning network and the alpha gamma rates into a single effective rate. And this is directly supported. And we can add more approximations like this directly to pynucastro following this lead. So here's a network that we use for thermonuclear supernova that supports helium and carbon burning. It has lots of different carbon endpoints, but building up to nickel 56, there's this alpha chain where you could do alpha p, p gamma with these intermediate nuclei, but we can approximate them out. So we don't actually carry these nuclei, but we carry the rates and we put them together into an effective rate that brings us between each of these nuclei. This is the code to write that network. List the reactants, some rates, because I didn't include neutrons, some neutron rates where I changed the endpoint and assume neutron captures fast, and then make APPG approximation to approximate out those nuclei. It approximates them out, and I can write out my network. We use this for supernova, and you could play around with the rates. So the nice thing about being able to easily build custom networks is you can then ask, are different things important to the physics? And so, for instance, are these links that bypass C12 alpha gamma important in the ignition of a detonation in the double detonation model? And they are. If we leave them off, the detonation proceeds much, it takes longer to build up, proceeds a little bit slower. If we include them, we're much faster. This is an X-ray burst simulation. This was done by, well, this is a 3D version of a paper by Simon Gouchandot. I know I'm not pronouncing that right. Hopefully I'm pronouncing it reasonably. It's a layered model where you have helium below hydrogen. The helium convection eventually builds up and ingests some of the protons, and you can see the whole layer expands. In MESA, he modeled this with the CNO networks. We easily can recreate CNO in pynucastro, export to C++ code. In this case, we evolved this network with an explicit integrator, and that runs 50% faster than doing our star implicit integrator on AMD GPUs, because this is only moderately stiff. We can export NSE tables, use those to capture the change in electron fraction at the center of a core collapse of a massive star as it's leading up to core collapse. So here's the evolving core. So we're actually keeping track of what's happening in the core using a big NSE table and coupling it to a network that's on the grid, and we're able to follow that evolution. All right, so this is my last slide. I'll stop here. We've built this library to be a Python library for nuclear astrophysics. We're interested in knowing what other features people would like. We think it's useful already for exploring different concepts from nuclear astrophysics, for learning about reaction rates, for knowing whether whether rates are needed in a network or not. You can do all this exploration inside of a Jupyter notebook. It's also great for education. I use it in my classes. And then once you're happy, we have backends that can export the code that can be used in simulation codes. We have a lot of things that we're hoping to add in the next year, and we'd love for more people to get involved as well. So I'll stop there. Hopefully I wasn't too far over.